Okay, so thank you everyone for this new I don't know, project from Zaiku group. Uh, and the idea is just like maybe we could like because we have like the in quantum formalism we are so far we are in the I'm presenting the quantum hardware course. But in the quantum hardware course, the idea is like um, we just like show the main types of the quantum quantum hardware computation that is present today in the literature. Models that people are trying to make the quantum computing. So we don't. In this course, we are not having too much like discussion about the meaning of quantum mechanics, different interpretations. We are following the traditional like Copenhagen interpretation. And I was talking with Bumblebee. Maybe it would be good if we have like something that we could like make more. Try to understand a little bit more the math behind the quantum mechanics and probably have different views of interpretations that we have today in literature. Because I think, at least I think, and I think other people also agree with me, that now we have a new type of experiment that is the quantum computing that can bring something different about like we could use different interpretations of quantum mechanics. Maybe this could be bring us in the future difference because so far, I mean, you have the experiments if you use like quantum optics. If you go in quantum optics laboratory, we have no difference. I mean, you have like the result that quantum particles or quantum all these quantum stuffs has, and it's hard to make a difference from the interpretations of quantum mechanics. So we basically you have the same math and you use the interpretation you want, that it makes no difference. But maybe in the future, with the quantum computing, all this quantum technology that is coming now, in the future, maybe we could have like a new type of laboratory that could give some difference between the interpretations, among the interpretations. So I was discussing this with the Bumblebee, and maybe it would be good, be nice if we start now, may have some sections discussing about the quantum mechanics interpretations, different interpretations, and so we agree, like we decide to give this name like quantum team because the British guys, the Zaiku group, is from the UK, and we decide like to have this it's like informal meeting, informal things. I'm not a specialist in quantum in different quantum interpretations, so it's a type of thing I'll be learning with you guys, and it's this. I mean, it's open. And if people we have the ideas, because in principle my idea is to give some lectures in the beginning. We have like we start like enjoying the different type of things. I mean, understanding a little bit different type of the quantum interpretations. And in the future, maybe we could like invite someone, a specialist in one line or different interpretation than the Copenhagen interpretation, that come to this meeting section and give some talks about to us. I mean, this is something in future, because I think it is good we learn at least the basic in the beginning a little bit. So I'll be learning with you guys. So I will like study a little bit some of these interpretations and bring here to presenting something, and you guys are open to make questions. If I don't know, I will just say I don't know the answer. And in the beginning, I will follow this. Because when I was trying like to when I suggest this to Bumble, I was thinking, okay, but I need to follow something. Otherwise, there's a lot of things spread around. And I'll decide to use this book that unfortunately we don't have English version. It's only in Portuguese. Teorias, the translation is Theories and Interpretation of Quantum Mechanics. It's from a Brazilian author. But unfortunately, we don't have in English. But it cits a lot of papers during the material from the book that I will use in every lecture. When I give one lecture, I'll give the references for you guys. And I think maybe before the lecture would be nice if I give the reference, because if you guys want to read something before, I think, and the reference will be in English. So because he based his book and he works with different interpretations, but I mean he always the book is based in a lot of different papers, papers that are written in English, of course. So yeah, so I will just use this book just to have to give me a guide. I mean, I will follow basically the book, and then after we have the idea of different type of how to interpret quantum mechanics in different ways, so we can like maybe invite someone, or if you guys want to one day present something. Oh, I read something in one book and I thought interesting. Maybe we could like I could give a talk about this. Would be welcome too. So this is the main idea. So I don't know if you guys have any questions now. It's open. Questions, comments.
I have one. If, I don't know if someone else has. I will prioritize them because we prioritize other guests. Okay, so you talk about the Copenhagen. I think everyone who's taken quantum mechanics course, the Copenhagen interpretation is the predominant. Maybe you can a bit start with my question is the difference between the Copenhagen interpretation and at the core compared to the other interpretations that came after. Actually, before that, what did maybe from physicists' point of view, what did they don't like from what was the shortcomings of the Copenhagen interpretation that physicists didn't feel comfortable with to then try to say, okay, yeah, maybe we need to find different interpretation.
Yeah, I would say that most of physicists don't care about the Copenhagen interpretation. Like they like, because it's the type of thing. The math is something like simple, because it's like we are treating with linear equations. But since the development of quantum mechanics is in the, let's say, 25, 26, Heisenberg, his work with matricial mechanics was 25, and Schrödinger was 26. And since that, I mean, people was like, the physicists was like working with the quantum mechanics, and has a lot of results coming that we are making predictions with the quantum mechanics, the tools that people has, and it's not so hard compared with general relativity, because general relativity you are using like nonlinear systems, nonlinear differential equations, and it was harder. I mean, especially in the beginning of the last century, because we didn't have computers, hard powerful computers to make the calculations. But in the case of quantum mechanics, it's like the guys like use all these tools, these math tools, and it's okay. I mean, it's like good. You have the results. The results agree with the experiments, and we are always like using these since then. I mean, and it has some let's say sociological things because you could use like quantum theory also to produce like weapons. And this was in the during the period of wars, and even after the Second War, we have like the Cold War. Yeah, that it's important to make development, uh, uh, technological development, and people didn't have so much time to talk about philosophy of the quantum mechanics. Okay, it's working this way, and it's the famous shut up and calculate. And the quantum mechanic is the Copenhagen interpretation for influence mainly for Bohr, the Niels Bohr, that is Danish and working in Copenhagen. That's why this name. And this was it's basically that you buy a quantum mechanics book. You will have it's this interpretation that is like 99% of the textbooks about quantum mechanics. So in fact, physicists, I think, like this interpretation, but the thing now, you have like new generation and we are in different contexts, and people were, oh, okay, but I want to understand a little bit more because the problem, I think now answer your question, Mahmoud. The problem, I think the main problem that especially Einstein didn't like it, a lot of people, even Schrödinger didn't like it about quantum mechanics is the thing related to the determinism of the thing. So Einstein thought that no, should be something missing. The theory is correct because it agree with the experiment, but something probably is missing, and other type of interpretations came even during this period, but was not. It's some few people that worked with this other type of interpretation. Most of the thing of the PhD, new PhDs that was being finished was like use this in Copenhagen interpretation, and okay, let's go. We have a lot of technological things to find, and that's was the view that came. Even if you go like to quantum field theory, a lot of new things there. The quantum field theory is a relativist, let's say, a relativistic version from quantum mechanics. It's more than that. It's just, yes, in summary is this, and a lot of things, new things that we were making the calculations and make predictions, and you find like new particles was like when with the development of large accelerators, people was like these particles that would be predicted is being found. I mean, in summary, it's a very successful theory, but today many of the people, scientists, believe that there is something missing, some interpretation. Maybe it's time to understand better this theory. And one of the problems, I mean, has a lot of successful things, but one of the problem is when related quantum theory with gravity, we cannot like make we're not able to join the most successful theories like general relativity and quantum mechanics. Someone raised the hand.
Yes,
Yes,
and I would like because I'm practicing quantum physics, and this is my area of research. This could be a big rabbit hole to go to figure out interpretations, but the important point to understand why is this interpretation successful is that actually they don't spend much time to dwell on the measurement process. All they say is relevant is before and after, and right now we cannot look in between, so let's not ask about it until we build a technology that you can start looking in between. And usually that's the kind of the biggest problem in quantum mechanics, the measurement process, what is happening and how it's happening. But that's why it's successful, very successful, because most of the time all you need is before and after.
Yeah. Yeah. And this is one type of thing that, I mean, the planning here, I will start with the Copenhagen interpretation and try to make, we have some experiments and try to understand in the Copenhagen interpretation view. And then we try, because I think even in textbooks, some textbooks just give like the calculations and not explain well what's behind this, even in the Copenhagen interpretation. So my idea is that, yes, one of the things that I'm planning in the future is to study a little bit about this measurement problem in the Copenhagen.
Can I make, because I sort of spent a lot of time, sorry to interrupt. Is there a procedure for interrupting or?
No, guys, go ahead. Yeah, please.
Okay, I studied this, and I think the reason why Copenhagen was so successful is because they went back to the original sort of core of Western philosophy, which is Kantian, the Kantian worldview, and he applied that to quantum physics. And I think a lot of the measurement, and it's 100% consistent with the whole stream of Western philosophy, as I think the measurement process came from von Neumann's work and a completely different mindset. So I actually think that the measurement problem is something that was created later, and that I don't agree that, maybe it did crop up in historical writings, but I don't agree that the measurement problem is a real problem if you actually look at, for example, the writings of Immanuel Kant or someone like that. And I think that's the reason why it was dominant, because if you had that sort of background, you sort of naturally would arrive at a solution very similar to Copenhagen. So that's why I think it happened. Obviously, Bohr had a schooling in philosophy, and I think it is very important, because I think if we're ever going to unite quantum mechanics and gravity, that we're going to have a much better understanding of the foundations of quantum mechanics, to be honest. Stop me if you think I'm babbling, because I think I am.
No, that's it. Good. George?
I'm going to take a rather radical point of view that I'm not sure we understand classical physics. It was just hinted that we have maybe a Kantian interpretation. But from my point of view as a mathematician, we're modeling our experiences with things that don't exist. Numbers don't exist. Infinities don't exist. Points don't exist. I mean, it's of course interesting that these models work so well, but I think sometimes we mistake the mental model, the mathematical object, for the reality.
Yes. So that's part of the Kantian worldview. The Kantian worldview is basically the view that you're in a pub and you get drunk and you say, I don't know if you guys exist. You could be all my figment of imagination. And Kant came along and said, oh, hang on. You have the external universe, which is essentially unknowable. Then you have like your senses, which in quantum mechanics become the measurement devices. And then you get the information from that, you analyze it, and you generate mental models. And that's very much the school that Western philosophy as a whole has followed for 300 years. And it's an extremely powerful model, because if you go back hundreds of years when the church was battling scientists, you're able to draw a division to what was religious information, what was scientific information, because the scientific information dealt with what you can measure and what you can see, as the religious stuff and a lot of the ethical stuff was stuff that was outside that model, outside the measurement and mental model process. So it's yeah, I'm babbling, I can't remember, but it's quite a powerful, I think it's very well understood from a, if you've got a bit of a philosophical background. And in that model, measurements are fundamental. Measurements are the primitives that you deal with. And so this measurement problem actually came later on when von Neumann did his mathematical modeling, and he says, oh, hang on, this waveform has to collapse. And at what point does it collapse? And then I apply it to the measurement device. But the whole point is that's not, the whole point is that's not really the physics. The physics, if you analyze it from a Kantian point of view, is you choose your set of measurements and you apply your mental models to the measurements, the information you get from those measurements. What von Neumann was doing was sort of blurring the physics and the mathematics together. So I personally believe the whole thing was created by mathematicians not following the rules of the physics/philosophy. I find it, as you can see, I'm obviously a Copenhagenist. In fact, yeah. Does that make sense? Sorry?
I'll just follow up on George. Sorry. Yeah, go ahead, please.
So I always kind of stay away from getting into philosophy because it seems that it's murky territory. There is no number that you can attach to a measurement there. But there are two important points when you are talking about this kind of tangentially. One, and this is related to George about classical mechanics, for example, and classical physics. It's actually the observation that we as observer don't disturb the system we measure. And this is quite different from quantum mechanics. So in traditional way, you try to actually isolate and minimize the effect on the system that you are studying during the measurements and study process. Because we are trying to be objective, it's independent of us, and we are trying to extract this information. So when quantum mechanics come to play, there's a significant difference, is that during the measurement process, you actually disturb the system. And this is completely different paradigm from the original effect that we as observers don't disturb the system. Now, there's another point that comes also on the mathematical side, is that usually classical mechanics and classical theories, they mostly work with smooth manifolds, that they were very successful there. And basically, when certain things have to be discretized, the states of the system, there's a puzzle. How would you describe this kind of discretized systems with this kind of smooth manifolds? Which actually perfectly well fits with the idea with the measurement process that you have this continuity before and after. And I will try to give example when people who are familiar with group theory. Basically, you have two systems that come together. They are representations of specific group. When they come together, now this is direct product of representations, but they could be decomposed in direct sum of representations. And basically it says that, well, before the measurement, you have this kind of direct product. After the measurement, you have to pick one of these direct sum states that you end. And this is similar to like rolling a dice. You have to roll a dice, and there will be a discrete value from 1 to 6 that will come out. So definitely these are kind of significant difference between classical and quantum. And I don't know how philosophy would get into this, because to me, the philosophical descriptions and definitions are not clear. They are mostly references to authorities and opinions. That's how I usually see and hear the philosophical statements.
Yeah, a lot of papers on the foundation of quantum mechanics aren't really that. There's somebody just pulling out some properties of the equations, or I think I was using fancy words to hide the fact they don't know what they don't have a clear handle on what they're talking about. I would agree 100%. But I can make some comments about the measurement process. the fact that one measurement can disturb, for better words, another measurement is actually not an issue, because the repeatability is the same measurement being made. That always happens, and that's fine in quantum mechanics. And in fact, I'll go one step further. You can actually define, if you, I've done some research in this, you can actually talk about defining your measurements in terms of your commutator relations and how it disturbs your measurements. Because if you think about a measurement as being a mapping to the real number line, because that gives you a complete ordering, then if you have a measuring device M, and you have another measuring device which is an arbitrary function applied to M, maybe a sine wave multiplied by it or something, and you're just looking at the raw data in a Kantian way, you cannot tell what the heck it is. You can't tell whether it's a measurement of momentum or anything else. And the way you can tell is by looking at the commutator relations and whether they remain invariant under certain concepts. So the whole quantum mechanics thing actually fits very, very well into the Kantian paradigm. It's just that it's, these days people don't tend to talk about quantum philosophy very well. Am I babbling again? I don't know. Anyway, I shut up and let you guys. Cool.
No, by no means. This is an open discussion, so everyone is welcome. I think Diego has his hands. Diego, welcome.
Hi. Yeah, first of all, thank you for putting this together. I think it's interesting to have a place where we can discuss different interpretations. Yeah, so the only comment I wanted to make, since we were talking about the measurement problem, is that, I mean, first of all, this is something that philosophers discuss quite a bit, and there's this new branch of philosophy, quantum philosophy, and one has to be very careful because it's very subject to the way you interpret the wave function. So you need to decide if you're treating the wave function in a realist way. So does the wave function represent something physical, or is the wave function simply telling me information about the statistics of the things I can measure, right? So you can think about it just as regular probability, where you just have statistics and you look at the numbers and that gives you results, or is it really something that is changing as the wave function interacts with the real world, right? And the reason this is important is because depending on how you make that interpretation, measurement plays a role in the way you treat the theory in terms of being local or non-local. So even if you treat the wave function as a physical entity and you see results that are non-local, it is well understood that there is a non-signaling theorem that prevents information from traveling faster than the speed of light, which is perfectly fine. But the problem is that when you write the equations for the evolution of the wave function, you're still seeing non-local events that if you're assigning physical properties, you can't describe in a real physical world. So you need to make that decision if your wave function, if you're treating it as a local physical entity or as a non-local abstract entity that just gives you information about statistics of correlations between different elements, right? And each of those two interpretations has its own set of problems. So you can't just pick one and say, this is the right way to do it. This is why people can't agree on interpretations of quantum mechanics. It's because no matter which one you pick, each one of them has its own set of problems, right? So even the Copenhagen interpretation can be treated both ways, as the wave function as a physical entity or as just information of statistics. And there's all these new sets of interpretations. There's quantum Bayesianism. There's what is it called? Relational quantum mechanics, and all of them have their own way of describing things. So this is a really difficult problem. It's not like saying, it's not as simple as saying, oh, many worlds interpretation, it has all these different worlds that you can never measure, and then we're just not going to talk about it, because actually many worlds interpretations has a great amount of explanatory power that you don't get from any other explanation. Now, it has its own set of problems, of course, but you also have to consider that one when you're talking about interpretations, right? So you can't discard, I would say you can't discard any interpretation at this point. And I mean, there's people that, their job is to do this all day long, right? So it's good to look into all of it.
I'm afraid I'm an egotist. I think Kant was 100% right. I think Bohr was 100% right. And that means that the waveform is mathematical entity. It is not one of the primary concepts of the Kantian world, which is an actual measurement. It's not a primitive object. So it is not real. That's my view. And I know I'm sure there's a big guy saying the many world view is right, or some other view is right, but that's my view. I think Copenhagen is clearly, it really is equivalent to it being a mathematical construct of the mind. I don't see it in any other way of interpreting Copenhagen, particularly some of the comments Bohr made. And sorry, I don't agree that it's, as I say, I don't agree that it's a difficult problem. If you follow the philosophical traditions, and if you believe that quantum mechanics and the theory of everything shouldn't be consistent with philosophy, should be consistent with philosophy, I think Bohr was 100% right. And it's not an issue for my simple mind. That's the way I'm always going to be, since I,
yeah, I mean, of course that's a point of view, but then you run into issues trying to explain why something abstract that is not physical can interfere with itself when you pass it through a physical set of slits, like in a double slit experiment, right? I mean, if it's just a construct of describing probabilities of physical entities, how can it do that, right? So yeah, I'm not saying it's wrong. I mean, there's ways to interpret that and all that, but I mean, it's not as simple as that, right?
well, I mean, the problem with it is it's a first level construction of the human. It's at the lowest level, and something that's theoretical but models your measurements 100%. How could you tell if you focus on it that it's not real? Because something that predicts reality very, very well doesn't necessarily mean it's real. And that's very philosophical type argument. But yeah.
So yeah, that's a point of view where you're basically saying that you can't describe what's going on at the fundamental level, right? So it's Plato's cavern, where you only get certain projections of the shade or the shadows of the reality that's underneath. Yes. But then at that point, why would you even talk about interpretations? Then that's case closed, right? So
yeah, I think it's closed as well. I've got no doubt in my own mind. But maybe I could spend time trying to convince you guys if you really wanted me to. But I think the original question was, why did Copenhagen dominate? And I think the large part of it was that it was very much in the tradition of Western philosophy and Kant and so forth, going back over all the conversation back. And if you follow that worldview, I don't think there's much room for issues like the measurement problem.
Yeah, I'll make one last comment and then I'll mute myself. The only issue I see with that interpretation or that way of thinking about things is that there is still a problem with locality or non-locality when you write down the equations that describe the evolution of the wave function. And I mean, it will require an example to show what I mean by that.
I understand what you're talking about. You're talking about entangled particles or something like that.
Yeah. More specifically, you know, if you look into, you know, quantum computing and you look at the quantum teleportation protocol, right, where you prepare a quantum state in one part of the universe, and then you perform a measurement in another part of the universe, and then you have that exact same state there, right? Even if you treat everything as just information of probabilities, there's no way to explain that. How did it get from one place to the other using that interpretation? And you can say, well, yeah, but it doesn't violate relativity because you can't communicate information. But still, the equations show that it showed up in a completely different part of the universe. So it's non-local, and then it won't be able to match with general relativity, right? So that's the only issue I see with making those assumptions.
Again, if you actually go back and you start sort of along the Kantian view, and you can actually kind of build up mechanical equations, they don't have space in them at all, and it's difficult to even construct the time. And so the equations of quantum mechanics don't depend on space-time, on space anyway. And if it did, you'd have a problem, because then you wouldn't be able to do quantum gravity by assuming that, you know, the continuum of space-time is actually discrete, or maybe have some other structure. So the fact that you can, provide you have some sort of symmetry, the equations do that, doesn't particularly bother me, because if you believe, as many physicists do, that space-time is an illusion, then the fact that you've got this mysterious behavior just falls from the earliest, or the most primitive forms of quantum mechanics, which is primary, which is more primitive and more primary than whatever the construction of space-time really is. Does that make sense? Yeah, anyway.
Yeah, it makes sense. The last thing I will say is that that's a way to interpret it, right? Saying, you know, you can't define space-time and all that. But if you take the many worlds interpretation, there's also a way to explain it very clearly. And of course, it comes at the expense of having to believe that you know, there's a splitting of universes, right? So.
And how does it split along what line? You know, what's the boundary where it actually splits? There's all sorts of issues with many worlds. Even what probabilities mean in a many world universe.
Correct.
So,
yeah. So that's the issue. What do probabilities mean?
Yeah. So. Yeah. Like I said, yeah. For me, I have made my mind up many years ago. So, sorry.
No, okay. I mean, this is the spirit, but I mean, I think Dimitri has raised the hand before George.
Yeah.
So.
Hi. Let's see. So I wanted basically to insert my personal opinion on what Guillermo was saying, and I think we largely agree. If not about the many worlds interpretation, but rather the world of many interpretations of quantum mechanics. So my point of view is pragmatic, and it's a little bit pessimistic. I don't believe that our brains have evolved sufficiently to be able to understand the world as it is. I think we can only understand certain projections of the world that we can analyze with our tools, including mathematics. And as such, no interpretation that we can ever arrive at is correct if you assume my axiom. Consequently, my pragmatic point of view is that the only interpretations that matter are the ones that allow us to derive new conclusions, find new things about the universe, give us a better projection of the universe. So I tend to think that if an interpretation is to be valuable, it has to go beyond philosophy and offer some mathematical language that will help us derive something new. That's essentially, and this is why I was looking through the interpretations, various interpretations right before this meeting. I got hung up in the stochastic quantum mechanics interpretation because it is a novel mathematical approach to it, and one that I haven't read enough about to understand it yet. Anyway, that's all I had to say. And I think, I mean, if we sort of agree on the pragmatic viewpoint, perhaps we can narrow the discussion by starting with the interpretations that have the potential of giving us something new to work with. That's all I have to say.
Okay, thanks, Dimitri.
I tell you
George?
one thing. Sorry, I'm just going to
yes,
say
George?
this.
Thank you. Yeah, Dimitri had actually said much of what I want to say. I also want to thank Edward for clarifying the philosophical background. My point I'd like to try and make is what is the difference between a theory and an interpretation? And I'll throw this out there along the lines of what Dimitri said, that if you can make a different prediction, then your interpretation is potentially a theory that's different. But if your interpretation doesn't predict anything different from what I'll just call the null hypothesis, Copenhagen interpretation, then it is just philosophy. So I think that's where I would draw the boundary between the physics and the philosophy, is whether, as Dimitri said, in practice it makes any difference what your interpretation does.
I think that's the shut up and calculate philosophy. Can I say one thing? If Copenhagen is right and the Kantian view is right, and you say that measurements are actually a result of getting a real number on a number line, so you can, and that's your definition of measurement, it's very, very difficult to see how string theory is consistent with Copenhagen. So there's an example where a philosophy says this approach is highly unlikely to be consistent with the core philosophy of quantum mechanics. I mean, that's an example. I think if you're going to look at other issues as well, you know, particularly quantum gravity, you are going to find similar situations where approaches appear to be highly, I wouldn't say absolutely impossible to resolve, but they're going to have certain philosophical implications. So I don't think the value of philosophy is there's going to produce a different explanation, interpretation, because interpretation is only going to survive if it gives the same results as quantum mechanics. So all the interpretations are going to give you the same results. What the value of interpretations of philosophy is to give you a sort of compass on your way to search through all the possible values. If you looked at relativity, they already had Lorentz contractions and all the rest of it floating around before Einstein came along. But he took what might be called a philosophical approach, saying, well, is any speed special? No. Speed of light should be constant, and then looked at that going on. And the same is true is thinking about relativity, of general relativity and so forth. They were, to some extent, inspired by his own personal philosophy, or a philosophy, which you might call a philosophy. And I think the value of them is that it's more of a compass than a definitive statement, and that's how I would view them and why I think they're important. And I don't take the view that shut up and calculate will, in the long term, get you the answers. Once we get to the point where experiments and building bigger and bigger accelerators become difficult, we're going to have to start thinking about philosophy more than just crunching through the equations. Although I agree that there's still a lot of work, engineering work and physics work to be done, I do think that the philosophy is important, and it's something we currently undervalue in physics.
Okay, so some people wrote something during when you guys was talking, but I don't know if Mohammed Reza, Sebastian, if you guys want to open your microphone and make the comments, because I don't know exactly when you write this. Mohammed Reza, for instance, you wrote here, Wigner's friend seems to attack the Copenhagen interpretation. The strength lies with the observer who both observes and is being observed symmetrically. It seems to be a comment. I don't know if it was. Oh, Mohammed Reza just wrote saying that it can't talk now. It seems a comment, right?
Yeah, I think it's a comment just saying that
About
the Wigner's friend's paradox is a criticism, or not a criticism, but it shows inconsistencies in the Copenhagen interpretation. I think, I'm not sure if Wigner's friend is a problem. I think the extended Wigner friend paradox is the one that shows inconsistencies in the Copenhagen interpretation.
someone raised their hand.
Yeah,
I think it was Sebastian.
yeah, but because most of these comments are mine, I tried just to write it because I had my son with me, so it could be hard to say.
Okay.
And in my opinion, because I put some comments like that, why Copenhagen interpretation? Because in my opinion, this is interpretation we have in which we have less classical things in this interpretation, and other kinds of interpretation just try rebuild and add some classical points of view, like many words interpretation or Bohm interpretation. Why we need many words? Because we live in words, but what is it? And the main reason why this intuition of quantum mechanics is not great, because we must remember that before the quantum mechanics, we have classical physics. So everything was classical. You can compare it as Aristotle's thinking. Yes, that physicists about 1,500 years don't neglect Aristotelian physicists. So you see, this is the same situation. Our intuition, classical intuition, is just bad. So this is my one point of view. And the second is that I cannot agree that we say that quantum mechanics is statistical. No, it's not statistical, and it is not probabilistic theory. You can show mathematically pure that this cannot be probabilistic theory in Kolmogorov sense. This is also important because we interpret everything in probabilistic theory, and probabilistic theory is connected with function. And you can see also that before quantum mechanics, there was no other kinds of mathematical tools or mathematical things like functions. So today you can say, okay, we can do everything by AI. What is AI and deep learning? It's searching of function. So the things, in my opinion, the mathematical tools has also real influence in our intuition. And in this case of quantum teleportation, this is tricky, and this is not true that this is strange, because you can, okay, you send one particle in one direction and the second particle in the second direction. They are entanglement, but you don't read them, but you use them to put information from one particle to the second particle. So we don't have two particles, but four particles. And the main question is not how it is possible that you put this information from one side of the universe to the second part of the universe, but okay, what you teleport is information about what is wave function of this vector value, and you assume that, okay, every system which has the same vector is the same system. So this is how teleportation, quantum teleportation works, that every kind of particle is the same because it is described by the same vector in Hilbert space. Yes. So I want to ask you, Edward, have you ever seen vector of position and momentum? Because why we think what is real or what is not real? If I want to describe classical system, I must put position and momentum as a 6-dimensional vector. It is real or it is not real? And maybe
classically,
this will be enough for this time.
well, Kantian model still holds, except you would expect your measuring machine not to you'd be able to theoretically measure the position and momentum at the same time at infinite degree of precision, theoretically, if you're smart enough and could build a proper machine to do so. So the Kantian model still works. It was actually coming into existence about the same time as Newton as well. So if you have a Kantian worldview, then the world is this horrible thing. Not horrible, but it's a thing that you can't actually interact with except through your senses, which in modern QM measuring devices. So it's no more or less real than anything else that you think about, but ultimately it's a mental construction. I hope that helps. That's from the Copenhagen view.
Okay. Okay, good. So we are almost 1 hour here. So I mean, the idea is exactly like that, but I mean, because we have like a lot of things, different interpretations. So what I'm planning today is like just an introductory thing. So it's very nice. I didn't know that the people would like talk a lot like that. That's why I make some slides, and I really like it that you guys participate a lot. I made some slides, but I'm not sure anymore because it takes too long time. I'll just show here a little bit just to give you the idea, because the idea I will bring something, and after like it's some slides with like, let's say 20 minutes with slides, and then after that we can make some discussion. Otherwise the thing will be too spread maybe, and we try like to have a focus in something, at least in the beginning. But today the idea was exactly like that. I prepared these slides just in case like you guys was too shy and okay, we'll be like here. So I prepared the things, but you guys is great today. So this the spirit, but to the things don't be too spread. I will always like try to bring something, and we will discuss about this thing. And in the beginning will be like the Copenhagen interpretation. Like today let me share just to give the idea. I'll not show anymore because of the time. It's almost 1 hour. So let me just share what I have prepared. So this is, in fact, this is the I will call this. This is the thing that we prepare using Bohm they prepare using like was one of these AI things that related.
Yes, DALI.
DALI, yeah, using DALI, and the equations.
Yes.
DALI don't know well the equations on quantum mechanics.
Exactly. So forget all the ignore the equations.
Yeah. But this is the idea. So I had prepared this just in case that you guys was too shy. That's not the case. What was great. But here just very quick. So I have prepared some introduction, talk a little bit about the Copenhagen interpretation, and show the double slit experiment. And we will try like to use Copenhagen interpretation. The math is very simple, just to tell what Copenhagen say about this experiment, and we'll discuss. And in the future, we will have another interpretations to discuss, like the double slit experiment and the Stern-Gerlach experiment and so far. So just give a view, like the introduction was talking something about the philosophy that Edward mentioned, the idea, the philosophers behind, I mean, the Copenhagen interpretation. But I can do this if you guys, and this is the thing, I will talk a little bit about the postulates, not give the details, and the double slit experiment, and I'll make some calculations, and in the end we would talk. We'll talk something. Just simple, very simple things, and we will have the discussions after that. But if you guys like want, before I have everything like prepared, maybe next Thursday, because the idea is not every week, not to have every week session. It'll be something like once or twice per month. But because today was like just the introduction, if you guys want, I can bring next Thursday. If you guys want to come, would be great. And I'll present the slides and we have the discussions. I mean,
thank you very much for putting up with me. I gotta go. My wife's at me. So, all right,
okay. Okay, yeah.
See you.
Let's go to bye.
So bye. So next week, maybe, if you guys want, I can bring the slides and we have some, about 20 minutes, it's simple, and have some discussions about the double slit experiment in the view of Copenhagen interpretations, and then we can talk, like, if you guys know different views, and we can talk about it. So, okay. Next Tuesday.
Yeah, I like the idea of bringing in a specific thing like experiment and these things, and then putting an interpretation on it. Yeah. In this case, with Copenhagen, and then see. I think it was Diego who put it about how important it is to choose what the meaning of, say, for example, the wave function, for example, what does it mean, and this type of stuff, In this case, you can putting it in the context of one specific experiment and then opening up a discussion. I think that's a good idea.
Yeah, I mean, the idea, George, is once or twice a month, but because I prepared these things today and I didn't show, if you guys want next week, would be because I don't need to prepare anymore. I have the slides already. So exceptionally, in this week would be like twice. But in January, when we restart, once, twice a month, maximum.
So, one thing I wanted to follow up on George's comment. George, is it fair to say you are from a philosophy of mathematics, you are a formalist? So the mathematical objects are done from a formalist point of view, they're just constructions. But we have also the Platonist, whereby the object actually exists. So technically, from their point of view, maybe the wave function actually exists somewhere.
So
Hilbert space is there is a Hilbert space somewhere in a universe or something. Maybe you want to make a comment on that, George.
It kind of relates to my comment about philosophy in general, is it only matters when it makes a difference to the math. So I don't know that there's any practical difference between a Platonist and a formalist point of view. There is a difference with the intuitionist point of view, which has a radical approach to the logic. And that's very interesting in its own right. So I think I wear different hats depending on what I'm doing. when I'm actually doing math, I feel like a Platonist in that the mathematical objects seem real to me, and it seems as if I'm manipulating the same way I manipulate real objects.
So maybe the similar thing that physicists in the lab, when they are preparing their system, huh, Carlos? I don't know.
We don't see Hilbert in the lab. Hilbert spaces. Yeah, but yes, so it was great today. I mean, thanks everyone.
Just one comment, if I can, because
Yeah, yes.
you prepare a system, not state of the system. Yes.
Yeah, yeah.
Maybe this is answer.
Yeah. So yeah, so it was great. Thanks everyone for participating. So next week, I one more questions. Sometimes I'm trying to make some calculations. Maybe I don't know if you guys have something. If you guys don't like the math, so if you guys don't like to see, but I mean it's not long calculations. The long calculations will be in the quantum hardware course, but some small like to explain the double slit experiment, I would make some calculations using the postulates. The postulates based in the quantum, in the Copenhagen interpretation. But if you guys have something against, so I could avoid the maximum. But I at least me, I like to use a little bit of math.
Well, we actually encourage mathematics. That's why
Yeah.
formalism. So we shouldn't run away from maths. Yeah.
Well, because I was thinking maybe there are some philosophers here that don't like to see the math.
Well, then it's the wrong room to be.
Okay, so I will use the math. Good. So okay, I think Diego raised their hand, please.
Yeah, just maybe a suggestion for a future meeting. So there's an interesting proposal from David Deutsch. As you know, he's considered one of the fathers of quantum computing. He has this thought experiment on how to test the Copenhagen interpretation or collapse theories against the many worlds interpretation. So that might be an interesting section to have, because the idea is a very simple Mach-Zehnder interferometer experiment where some of the mirrors are connected. So a bit of history. Actually, it was him thinking about this that drove him to think about the first quantum computing and develop all the theory for quantum computation. It was him thinking, how can I test the many worlds interpretation? So I think it's an interesting experiment, and then we can discuss if it's, if it really is a good experiment to prove that the many worlds or the collapse theories exist or not.
Yeah, this is the idea. So my idea in the beginning is we have understand a little bit about all these interpretations. So we'll start with Copenhagen because it's and then we'll talk a little bit about Bohm and many worlds and other type. But when we talk about Copenhagen in many worlds, we can like stop. Okay, not see another interpretation now. Let's see what people are discussing about this. So this is. Yeah, and you have an experiment, even a thought experiment in mind. This would be great to discuss. But before we need to understand everyone need to understand a little bit. At least the basics about the Copenhagen. People know more about many words. People know because but if you see the math and see what the reasons, they interpret different the math. So I think would be better then and then after we discuss the Deutsch suggestion. Okay, more? Someone Someone else?
Yeah, I just want to say it was great to have this sort of opening session where we can actually test the audience. To be fair, I was also similar to you, Carlos. I thought people would be more shy, but this is actually great.
Yeah.
It turns out people are willing actually to share, which is great. So well done to everybody, those of you intervened. It's great. This is an open forum. There's no right or wrong. This is the reason why we created this. So well done to everybody for and I hope you continue to contribute with your insights, your views as well.
Yeah.
Well, I want to say great that you all wanted to come together and meet like this for this tea. I'm looking forward to our next meeting, but unfortunately now I have to go to another session.
No, okay.
Nice meeting you all. Bye.
Okay, bye. We are already finished. Okay, so this is the idea, about 1 hour per month, or once or twice per month meeting. I bring something and then we discuss, just to have a guide, and after I show the things, we can talk with different interpretations. If you guys know. The idea is the next meeting, I will bring the double slit and see the Copenhagen interpretation view, take some calculations, it's not complicated, at least for people that they use it with the quantum mechanics things. And then we have a discussion, and if you guys has another type of interpretations that has this other type of interpretation says that side that you calculate there means a different thing. So, okay. So thanks a lot, everybody. So see you next Tuesday. And people that are following the quantum hardware course, this Friday we'll have another section. So bye. See you. I'll stop. I think you need to stop recording.
Yes. I'll do that now. Let me stop. Yeah, it should be stopping now. So yeah.